This Thursday will be test number 1. I will start promptly at the top of the hour. I'll try and get here early, but who knows with traffic. I'll shoot for at least 35, 40 minutes early. So if there is an accident, I'll still be there on time. All right. What I'm going to do now is my world famous review for the next test, caveat. And that is, once in a while, I might forget something in a review. I try not to, but that happens. If I've talked about it at least twice in lecture, it's fair game on a test, even if I forget about it in a review. But I shouldn't rush. This last time I don't walk on water. And in fact, one of your colleagues has pointed out a mistake I made yesterday when I was rushing putting up a structure, which I'll correct tomorrow. All right, let's go through. Start out the semester. With hydrocarbons, I assume everybody here can read cursive, so I'll do some writing on the board. What's a hydrocarbon? Hydrocarbon is a molecule with only carbon and hydrogen atoms. When we talk about hydrocarbons, there's two types. First type is a saturated hydrocarbon, you should know. Saturated hydrocarbon is a molecule with only carbon and hydrogen atoms and only carbon-carbon single bonds. The other type of hydrocarbon is unsaturated hydrocarbon. An unsaturated hydrocarbon is a molecule with only carbon, hydrogen atoms, and at least one carbon-carbon double bond or triple bond. Next, I start talking about the alkanes. Speaking about alkanes, did anybody drive by a gas station and think of alkanes? I see a few of you. Oh, I'm working on you. It's working. All right, alkanes. And the alkanes are acyclic saturated hydrocarbons. Acyclic means not in a ring, not in a circle. And then I talked about the cycloalkanes. And the cycloalkanes are cyclic, meaning can be in a circle, or are in a circle, saturated hydrocarbon. And these are all good definitions you should know. Normally I don't ask definitions, but I think these are very key to learning organic chemistry. Hint? All right, next thing I did was showed you how to draw alkanes. And I showed you there are 4 bonds to carbon. Remember Thursday, that's your friend. When you draw anything down, make sure you always have 4 bonds to carbon. Does this look like some 3D coming right at you? Hope it is. And I showed you how to figure out how many hydrogens by knowing there are always 4 bonds to carbon. This carbon has bonds there. That's 2, 4 minus 2, 2 carbon. I showed you how to draw the cycloalkanes. And that's every bend in a line is a carbon, and we use polygons, polygon shapes. This is 6 carbons, and you learn later on what that's called. 5, 3, and 4 I showed you also. Example, you call this a square, I call that a cycloalkane with 4 carbons. Glad I have slides. Anyways, next I talked about, excuse me, getting all choked up about this stuff. But anyways, next, look out, my sense of humor is coming out. But anyways, next I talked about how do you name these. I talked about the IUPAC names, which are the official names, which we call IUPAC nomenclature. And there I talked about how IUPAC came up with carbons 1 through 10, the alkanes. Are given names. 1 is methane, 10 is decane. And I have on Blackboard and in my notes, both there in a separate file, a table 1 through 10. And I said, I highly recommend you know these like you know your first name. Next, I showed you how, if we have a long chain and there's something else on it, we call that a branch or a substituent. I talked about the alkyl groups. You have a CH3 attached to a ring or a long chain. It's your old friend now, the methyl group. There are rules how to come up with it, but it's easier just to memorize them. When you have 2 carbons, the carbon at the end ended bonded to a ring or a chain, and that's called ethyl. When you have 3 carbons, there's 2 possibilities. When it's to the end carbon of 3 carbons, that's called N-propyl. Even though I capitalized it, it's all small case, but since none of you are going to be keyboarding on my test, you shouldn't be, because you're going to be writing it. If it's upper or lower case, works for me. When it's 3 carbons to the center carbon, it's called isopropyl. There are 3 butyls, 4 carbon. I've only asked you to learn 2. When you have 4 carbons and it's to the N carbon, that's called now N-butyl. And by the way, the N is lowercase. Later in the semester, I'll show you where uppercase or capitalized N is used for something else. And then when you have 3 carbons to the center carbon, and the center carbon is bonded to something else, it's called a terbutyl, which is short for tertiary, or as I've already started doing, and you put either one on the test, you can call it T-butyl. And Dr. White loves T-butyl groups, and I really like isopropyl. They've been nice to me, and I've been nice to them. And I showed you how to do rings. and chains, how to find the longest chain. I've gone through that in a problem set. But one thing I do want to remind you, what would be the IUPAC name for that? Well, you count how many carbons in the ring. 5, I hope you all counted that, 5 bends. 5 is pentane, I hope you know that. Common mistake on test number 1, which I'm telling you about so you don't make it, is people forget to put cyclo. When you have a ring, it's cyclo, so this is cyclopentane. Don't forget to put that. If you just put pentane, I'll mark it 0, because pentane and cyclopentane are different. The only chemistry I talked about, which was, in my mind, boring, but at the same time probably one of the most important reactions we do right now in our planet. Wars have been fought over stuff because of this reaction, and that is, you take an alkane or a cycloalkane, react with oxygen, you need a little spark or a heat source, combustion, and you get carbon dioxide and water. And I have problems on the problem set for that. And where do we find alkanes in our life? Remember on test number 1, I have 10 points in general knowledge. Methane, natural gas. Propane is used for one way of your barbecue. Octane is used in gasoline, major component. The isomers of octane are about 50% of the weight of gasoline, which is why I've been telling you, when you go by a gas station, think of alkanes. Then we have Vaseline and baby oil. Yeah, you can smell it, right? Our higher chain, longer chain alkanes, and same thing with pair. Paraffin wax, which makes up half the weight of a candle, and that's the alkanes. Next, I talked about the alkenes and alkynes. I'll do the alkenes first, and that's a double bond. How do you tell a double bond? 2 lines between 2 carbons. How do you name this? Find the longest chain or ring that has both carbons of the double bond, name it as an alkane or cycloalkane, drop the ANE ending, and replace it with ENE. And then for acyclic, meaning a straight chain, you need a number. What's the lead carbon, the smallest carbon nearest to the end. Remember, heads up, when you're doing a test on Thursday and you're numbering a chain, only start from the ends. Common mistake, students start from the middle. You can only start numbering a chain from the end. You need a number. When it's cyclic, no number, because one of the carbons in the double bond, the ring is going to be 1, the other is going to be 2. when you have a double bond, which we do, and remember, I'm showing bond angles, and you should too. This carbon is connected to that, to that, to that. 4 carbons is butane. It's a double bond, drop the ANE, and ENE, butene. It's acyclic, so I need a number, 1, 2, 3, 4, 1, 2, 3, 4, 2 butene. But now I taught you when you have 2 groups or 2 atoms, 1 on each carbon of the double bond, like hydrogens or CH3, and if you have a plane orthogonal, or like your hand or on a test, your pencil, and it's on the same side, below your hand or above, on the same side, we call that cis. Therefore, it's cis-2-butane. If it was opposite, that would be trans. When you have 2 hydrogens or groups that are the same on one of the carbons, double bond, you have neither. When we look at the chemistry of a double bond, it's important that it has 2 bonds and they're not equal. One of them is a pi bond and the other is a sigma bond. Pi bonds, ooh, it's broken there. It's broken. That's better. Anyways, I'll have to work on that practice tonight. Anyways, pi bond, break, there it is. Pi bond I can break easily, sigma bond I don't. First reaction I showed you. We take a double bond reactor with hydrogen gas, H2, and a catalyst. You break the pi bond, not the sigma, and each carbon double bond gets a hydrogen. And that's anytime you see that in a molecule, in a double bond. You have a double bond, you break the pi bond, and each carbon now gets a halogen. X is used as the halogens, chlorine, bromine, or iodine. Halogen gas exists in nature as a diatomic molecule, X2 or Cl2Br2, and you break each pi bond, and each carbon, or the pi bond, each carbon of the double bond gets a halogen. Now, these are symmetrical addition. You're adding the same to each carbon of the double bond. When you have unsymmetrical addition, when you're adding 2 different things to the double bond, and we look at this reaction, and remember X here can be chlorine, bromine, or iodine. I've never seen it with HF. It'd be pretty dangerous too. But anyways, you break the pi bond. One carbon gets, the double bond gets the H, the other gets the X. How do you know which? Markov-Nichols rule. The carbon of the double bond with the most hydrogen gets the H, the other carbon gets the halogen. In other words, the rich get richer and the poor get poorer. Them that has it gets it, and we're talking about hydrogens, not dollar bills, or 10 or hundreds. Same thing, but now you use an acid catalyst. H plus means any acid, like sulfuric or anything on my test. I'll use H plus. ACS sometimes uses H plus or H2SO4. And you react it with water. Think of water really as H and OH. You break the pi bond, one carbon gets hydrogen, the other gets hydroxyl, and again, this follows Markov-Nichols rule, which the carbon of the double bond with the most hydrogens will get the hydrogen from water, the hydroxyl group will go to the other carbon. Oh, before I continue, someone yesterday had a question I should answer. The question was on Thursday, after the test, is there a lab? And the answer is yes. All right. Next, I talked about triple bonds. And a triple bond alkyne is denoted by 3 lines or bonds between 2 carbons. And this has 2 pi bonds and 1 sigma bond. Nomenclature, find the longest chain with both carbons of the triple bond, name it as an alkane, and then drop the A in the ending and put YNE. And you need a number. And the number is what's the lead carbon of the triple bond closest to the end of the chain. Now, I have never seen in the last, number of years, I won't tell you how many, anything where I've ever seen a triple bond except once, eons ago, in a paper, in a ring. Therefore, it's just not going to happen in my life, and it hasn't. It's not going to happen in yours, so you don't have to worry about it. There's no cis-trans isomerism, since the triple bond, did I say double? I meant triple bond. The triple bond is linear, is 180-degree bond angle. Thank you. Now, when we have a triple bond, we have 2 pi bonds. That's ugly too. That's better. 2 pi bonds, 1 sigma bond. You know what you can do? Oh, it's working now. You can break pi bonds like that, and therefore we have not 1 but 2. And when you break a pi bond between 2 carbons, each carbon gets a hydrogen. 2 pi bonds, each carbon gets 2 hydrogens. Since organic chemists are lazy, we are, and we don't want to balance stuff, we don't. Instead of balancing this, we put bracket X as close bracket, and whenever you see that, that means excess. That means you have all the reagent you'll ever need of that reagent to react whatever it can react with it. By the way, the catalyst is also, as with a double bond, nickel, platinum, or palladium. If you're in industrial chemicals, you use nickel because it's cheaper. Pharmaceuticals or research, academic research, use platinum or palladium, which is a lot more expensive. But that will never be on test. And you break each pi bond, and each carbon of the triple bond gets 2 hydrogens. Hydrogenation of a triple bond. If I take a triple bond and react it with halogen gas, remember X here is the halogens, fluorine, chlorine, bromine, or iodine. You break each pi bond, because there are 2 of them, and each carbon of the double bond gets a halogen for each pi bond, 2 pi bonds, each carbon gets 2 halogens. Since we're lazy, I don't want to balance it, I use again the abbreviation bracket X, letter S, close bracket, meaning I have excess reagent. All the halogen gas, in this case, that will react whatever halogen gas can react with. And each carbon gets 2 halogens. Oh, I just remembered something that I would have forgotten while we're talking about alkynes. The simplest alkyne which the IUPAC name is ethine, nobody ever uses it. The common name is acetylene. On the test, I'll never ask you, here's a molecule, what's the common name? But I will ask you, here's the common name, draw the molecule. So if on the test I ask you draw the structure of acetylene, that would be it. The reason I do it that way is you're likely to see common names on ingredient labels of things you use in your daily life, and you might wonder, what am I putting on my hands? And this way, you can think of the structure and then, I really want to do that? Well, you won't be putting acetylene. But as the semester continues, you'll be amazed stuff you use in your daily life and where it comes from. And safe, mostly. Next, I talked about aromatic compounds, compounds that originally were isolated from herbs and spices. I don't know, do you have any cinnamon? Did you think, ooh, aromatic compound? Or do you have anything with vanilla in it? You know, good stuff like cupcakes, or stuff with frosting, or vanilla ice cream. And think about, ooh, it tastes good because of an aromatic compound. It does. And the simplest one is benzene, which I can draw like this. I can draw the other Kekula form, which is another resonance form. I've moved the bonds, same thing, no, I haven't rotated it. Or I can use showing the pi cloud donut like that. I like these two because I just think it's cooler. But the third one is perfectly correct on my test, and these are all benzene. IUPAC in their infinite wisdom, and I mean that sincerely, chemists have used that name for that structure for eons, like centuries, and they said, no, we're not going to change them, we'll make the common name the IUPAC name. And the key thing with aromatic compounds is the fact that the stability of the pi clouds of the double bonds holding hands or electrons makes this a very stable molecule. And you don't want to break those double bonds, unlike those which you can't. Another name you should know, IUPAC took the common name. Is a methyl group on a benzene ring. It's not called methylbenzene, it's called toluene. When we have a dye-substituted aromatic, most organic chemists, like your instructor, use not numbers, but the following nomenclature. And that is, if it's 1,2 dye-substitute, I know aromatic, this is not for cyclohexane. Common mistake on test number 1, students use it for cyclohexane. That's wrong. This is only for aromatic, is ortho. 1,3 is meta, and 1,4 is para. At this point, I taught to you names of some new substituents. Fluorine is fluoro. Bromine atom on a ring or anything else really can be on an alkane, but I didn't teach you that at that point, is bromo. Chlorine atom is chloro. Iodine is iodo. And nitrogen bonded, which has 2 oxygens, is called nitro. And I showed you how to name those. We went through yesterday the problem set, how to do that. If you have more than 2 substituents on an aromatic ring, use numbering. Remember, the methyl group is considered an alkyl group substituent when you use toluene. So nitrotoluene would be nitro group here, and it could be ortho, meta, or pure. Question would be, what's the IUPAC name for the follow? Well, I'm going to let you try that out first. I'm going to share. I'll also give you time to catch up. By the way, we'll get later in the semester, you'll find out catch-up is heavily organic. All right, let's take a look at this. What do we have? Benzene ring. How do you know? 6-membered ring with 3 double bonds, conjugate, alternating double, single, double, single, double, single. Methyl group on it, that becomes toluene. Nitro group, nitro, toluene, 1, 2, 3, 1, 3. Oh, look, someone put a nice table on the black whiteboard over here, and that would be meta. So that would be meta nitrotoluene. And as I talked about yesterday, on the test, I think it's either 45 or 47 points, or what I call nomenclature. 2 main types of nomenclature problems. Here's the structure, give the IUPAC name. The other one is, here's the name, draw the structure. And we practice all those. Oh, and hopefully you've done it on your own too. Now, when we look at reactions of aromatic compounds, as I mentioned in class, I will not be teaching you directors in class. When there's something on there directs it where on the ring to go. I'll always, on test number 1, just gave it away, start with benzene. So these are the only reactions, always starting with benzene. And the first one is halogenation. I can't ever remember, but I haven't really worked much in this area, say fluorine. And here you need a catalyst. And halogenation with a benzene ring aromatic undergoes not addition, where you break the double bond, like in alkenes. It goes through a substitution reaction, because in a benzene ring, you do not want to break the double bonds, because that you lose the stability of the ring. Therefore, you replace one of the hydrogens, whatever you're adding. In this case, a halogen. And come to think of it, I don't even think I've seen it with iodine here. And that would be the answer. And you also get HX, but on my test, as you see, well, you will see, as you've seen on the problem set, I've asked you the organic product or products. On test on Thursday, be sure to read the problems, the questions clearly. I write them clearly. Take benzene, react with nitric acid, HNO3, and sulfuric acid. I showed you how this forms NO2+, nitronium cation. It attacks the benzene ring. Replace one of the hydrogens with a nitro group. If you put a 3 instead of a 2 there, I'll mark it wrong, because that doesn't exist in nature on a benzene ring. It's a common mistake on test number 1. Don't make it. You take a benzene ring, react it with sulfur trioxide, and next also sulfuric acid that reacts to form a cationic intermediate that attacks the benzene ring. And put a sulfonic acid group on, which I haven't asked you to learn how to name it, but I will use in class, so that's why I talked about it. Remember, that's SO3H, not 4 oxygens. If you take benzene, and my test, that's all we'll start with, react it with an alkyl halide, RX, R is anything with carbons and hydrogens, and has a halogen and one of the carbons. Halogens is normally chlorine or bromine, and use the catalyst aluminum trihalide. This is Friedel-Crafts alkylation, which I'll never ask you the name of the test, on the test of this reaction. And this is a wonderful reaction because it allows you to make something very rare, special, and nice, and that's a carbon-carbon single bond. And the bond from the benzene ring goes to the carbon in the R group that has the halogen on it. I'll say that again. The bond from the benzene ring goes to the carbon in the R group that's attached to the halogen. And you also get HX, but that's inorganic. Remember, organic chemists are biased against inorganic stuff. And that's everything that will be on test number 1. Any questions? In that case, I have 2 questions for you. How many found the review useful? Raise your hand. How many would like me to do it again for test number 2? Raise your hand. Well, you don't have a choice, it's in the syllabus. So now you've seen my world famous review. Let's do something interesting for a few minutes, and then we'll go back to alcohols if I have time. And the first thing I would ask you is, give the organic product or products for the following reaction. I'll give you 8.76 seconds. 8.1, 8.2, 8.4, 8.6. Time's up. All right. if we go over to, I have it right here, let's look at this. Question is, what's the organic product or products we're following? First thing you do is look for what's different. What's not a carbon or a hydrogen atom or carbon-carbon single bond. Ooh, double bond. No, two double bonds. And what am I reacting it with? Excess acid, which just tells me I have all the acid in the world I'll ever need to react with anything acid will react with. I have excess water, which I also have all the water I'll ever need to react whatever water can react with. Oh, I can draw water this way. And now I know that if I have a double bond, any double bond will react with acid and water to break the pi bond. One carbon gets the H, the other gets the OH, and it follows Markov-Nikolson's rule. Well, because I have two double bonds, each one reacts like it's alone, nothing new. And that's the beauty and strength of functional group chemistry and organic chemistry. You break carbon-carbon single bonds? No. 1, 2, 3, 4, 5, 6. I'm running out of room here, so I'll write it up here. Let's look at this double bond first. Which carbon of double bond has the most hydrogens? Time's up. 2. Markov-Nikolson's rule says the H from there will go here, the OH will go there. That's these two carbons. I'll come to this double bond, same reaction. And I'll say, have to use Markov-Nikolson's rule. Which carbon has more hydrogens in this double bond, 2 or 1? Time's up, hopefully I'll pick 2. Hydrogen goes to there, which is this carbon. Hydroxyl group goes there. And that's what you have. And that's the nice thing about organic chemistry. If you have more than one functional group, unless they're close together, which I won't do in this class, and that becomes special cases, it acts like it's alone, which is what I just did, both ends. As I mentioned, on test number 1, I will have one and only one synthesis problem. Because if I do any more, that's cruel and unusual punishment. That's been outlawed by the Supreme Court up to now. I don't know what will happen in the future, but now it has been. And therefore, let's practice one. And on these, to help you out, if there's more than one starting material, I'll put question marks. That tells you you have to put down 2 starting materials. And the question would be, what would be the 2 reactants or starting materials I react with aluminum trichloride to make that compound? While I do that, and if I ever forget to send it around, I might do it first. See, it just come to the times. Quick, keep it moving quick. Remember, when you're done, look up and smile. All right, let's take a look at this. I think everybody's done. And we look at the product. And what's different? Ooh, benzene ring. Try 10. But it's not just a benzene ring, it has carbons on it. What do we use for carbons? And hydrogen? R. What am I reacting with? Ooh, aluminum trihalide. Chlorine is a halide. And X here can be chlorine or bromine. What do I react to do that? Benzene plus an alkyl halide. This is the fun part of organic chemistry because you get to make things. And the question is, what is a question mark? It doesn't matter which one you put first or second. One of them is a benzene ring. The other, what's my R group? The carbon's attached to the benzene ring. Which carbon has the halogen? The N carbon. And I can write it two ways. This will help you see it. What's my halogen? Chlorine. You could have also written it this way. On a test, if you do or don't put dashes, it doesn't matter to me. I just write it a lot of times to keep myself going straight across. And that's how you do a synthesis problem. Oh, let's do one more. What would be the starting material there? By the way, you're doing really sophisticated organic chemistry. I don't think it's that painful. That might be fun. Keep the sign sheet moving because we need to get everybody signed in. Quick reminder, if you're one of the 3 people, you see your name up there, make sure you get one of these and handed in today or tomorrow, especially before Thursday. All right, let's take a look at this because we're almost out of time. Keep the sign sheet moving, please. All right, what's different here? We have a halogen on a carbon, but we have an adjacent carbon with a hydrogen. And why do I want that? Because what do I have here? HX. What do I do? Double bond, HX. One carbon gets the H, the other gets the X. It follows Markovnikov's rule. How many carbons do I end up with? 3. Well, I'm not adding carbons, so I'm going to start with 3. The carbon with the halogen is one of the carbons of the double bond. You can write it this way. The same molecule, all I've done is rotate 180 degrees, would be this way, and that's it. And where's the sign-in sheet? Got 2 more rows. Those of you on this side, you can leave. Those of you, sorry about running late, if you haven't signed in, just wait a second or two. It's going around quickly. How quickly? Those of you have